Okay, everybody, let's begin. I may be a little less scripted and not go by the book as much, but we'll see. We'll see how it goes as far as the content, mathematics is concerned. We'll see what works. So let's begin. All my videos have been bad with audio, and I would like to change that. So, okay, well, let's break into the mathematics here. And the book, let's get the font pretty big where we can see it. I don't want to get too theoretical and go into the reals and rationals and all that. But I'll say a little bit about them just so you might have some motivation. Where my cursor is, the natural numbers, anytime we say that, we mean the counting numbers you count on your fingers, starting at 1. 1, 2, 3, 4, 5, so on, up forever. If you take advanced math, you'll get into all this stuff. And we put them in a set inside little swervy ellipses, and we call that set the natural numbers. The ellipsis is just a box that holds, the 1, the 2, the 3, and on up the chain. And there's an infinity of them, an infinity of the natural numbers, that is, on up to infinity. And the whole numbers are a lot like the natural numbers, except we put 0 in there as well. We start at 0, and then we count upward. 0, 1, 2, 3, on up to infinity. We never reach infinity, of course. That just means infinity means we go forever and ever. Now, when we say the integers, we mean we include things called the negatives. The naturals we call the positive. We call them positive. 0 is neutral. The things on this left side here are called negatives, or negative integers. So we have 0 here, we have positive integers. Again, I'm being quite fast here because I don't want to spend a whole lot of time here. This should make decent sense. But anyway, Now, the set of rational numbers, where my cursor is here, that's the set of all numbers of the form integer over integer. Integer m is in Michigan, divided by fraction divided by. A fraction is divided. So m over n, Michigan divided by Nebraska, where m is in Michigan can be any integer, and n is in Nebraska can be almost any integer except for 0. That little slash there means not equal to. N can be anybody but 0. N is not equal to 0 is what this right here means. Okay. Now, notice from the definition that rational numbers are fractions. You can also write them as decimals. But now when you write a rational as a decimal, it will either be repeating or it will terminate. If you write it, it's a rational number is you can think of it as a decimal that can be written as a fraction of two integers, m and n. Where, of course, n is in Nebraska on the bottom will not be 0. Now, okay, and that they indicate that here. Now, of course, it stands to reason if you have a number that's an integer, it's going to be rational, because if you have the integers here, like if you have, for example, positive 2, for example, right here. Excuse me. Well, it won't let me highlight it, but if you have positive 2, you can write that as 2 over 1, where m is in Michigan is 2, and n is in Nebraska equals positive 1. So, of course, the integer 2 is rational, and doing the same thing, doing the analogous thing for all these, they're all rational. Like negative 3 would be negative 3 over 1, where we could let m be negative 3 and n as in Nebraska be positive 1. So negative 3 is rational. All the integers are rational. 0 can be written as 0 over 1, and it's fine to let m be 0. M is in Michigan, and we let n as in Nebraska be 1. So they're all rational. Now, of course, hence, and from that, if you're a whole number, now if you're whole, you'll be an integer, and hence you'll be rational. And if you're natural, you're a whole number, and hence you'll be an integer, and hence you'll be rational. So things like 15 over 8, which equals 1.875, that is rational. We can tell it's 15 over 8, right? 4 over 11, it's immediately rational. It's a fraction of two integers. That's what it means to be rational. Integer 4 over integer 11, right here. And indeed, we get the repeating 0.363636. And notice with a repeating decimal, we put a bar over it. A bar means that it repeats that pattern of 36. So we have 0.3636, and we get 36s forever. I should point out, if you get an infinity of 36s, sorry, I've got my advanced math stuff up here. I need to get that put away. If you get an infinity of, let me get this up here. It's giving me a hard time. If you get 0.363636, a repeating, how do we write that? What if we didn't know what that was? What if they ask us to put that in a fraction mode? So what if they give us, say, insert equation, where's equation at? Well, can't find an equation. Hold on. I think I've got to go to the main word. Sorry for the delay, guys. So, well, if it's not going to cooperate, I'll just forget about it. Insert. Here it is. Sorry, they put it down here. Equation. And let's say, okay, we get 0.36. Go here to equation tools. Go to accent. Go to bar. Well, oops. I need to actually put it in there. So 0.36. So we got 0.36 bar. I don't want it over my decimal though. Yeah, like that. So 0.36 bar. And now here's the rule. It's 36, or here's how you do it. Notice that if that would have been just 0.36, it would have been 36 over 100, right? But since it's bar, there's a rule that says you subtract one. I could prove why that works. Just take my word for it that it does indeed work out. So it's 36 over 99. And you end up, of course, you can reduce it. Divide both top and bottom by 9. And you'll get 4 over 11. Because 0.36 without the bar would be 36 over 100, right? And whatever, you reduce it, but anyway. So 0.36 bar is 36 over 99. Like another example. So insert equation down here. So if we had like imagine I had something like, I want something that won't reduce. Well, yeah. Something that would be stubborn, well, or at least, this might reduce actually, but I don't want to fool with it. So if it does reduce, we won't worry about it. Notice that 0.367 equals 367 over 1,000. So if I insert the bar, so go to equation, I don't know, insert equation. I need to make it big. Equation tools, accent, bar, put my decimal outside the bar, put my 367 here. Now that's going to equal 367 over 999. And you might could reduce that, truth be told, but I'll leave it to y'all to reduce it. But the whole point is you subtract 1 from 1,000. The 999 came from the fact that we subtract 1 from 1,000, right? If we want to do something more plain Jane and everyday, what I could do, something a little more humble, I could go to insert. Insert equation. I forgot to hit equation. Yeah. And equation tools. What about just something more everyday? 0.2. Well, that's 2/10 because we go to the tenths place. Notice with 367 we went to the tenths, hundredths, thousandths. We divided by 1,000. So with 0.2 we go to just the tenths place. So it's 2 over 10, which is 1/5. So 0.2 bar. Let me get the bar symbol. Accent, bar, well, humbug. Let me get that. 0.2 bar. That's 2 over 9, because 10 minus 1 is 9. Well, that's good. Okay. And 2 over 9 won't reduce, and so that's good. And y'all get the idea. And these are all rational numbers. And before I come back to the book, let me just point out, there's plenty of things that are not rational, so don't get the wrong idea. What if a number is not rational? There's things that cannot be written as an integer over an integer. You might be inclined to think that everything can, but that's not true. There's irrational numbers out there. So if I insert equation, roll the screen back up, equation tools, well, the number pi is not. Euler's number E is not. The golden ratio of geometry is not. But these are kind of out there. What about something that's not so out there? I tell you what about the square root of something that's not so clean, that we can't clean up? Like the square root of 9. Now we can mathematically sort of sweep that up. That's 3. So that is rational, right? And we, everything is well. But like if you did, if you did the square root of like 25 over 9, you just take the square root of top and bottom, and that'd be 5 over 3, and that's rational. But here's where most square roots are not, though. Don't get spoiled here, right? What if we did something like the square root of, we don't have to look far, the square root of 2? Uh-oh. There's no way to write that in a pretty way. That is irrational. Because, you can't write that, you can't make that pretty, right? The square root of 2, there's no making that pretty. Most square roots cannot be simplified nicely. Most square roots cannot be simplified so nicely, right? You just can't, So the square root of 2, the cube root of 2 is irrational. The square root of 3 is irrational. A lot of cube roots, the fourth roots and all that, they're all irrational. But yeah, now here's the thing. If I go to, let me go back to it. I wish the equation editor was a little easier to get to, but it is what it is. If I go back